What if I told you that in 2017 humanity received its first confirmed visitor from another star system, and we almost missed it completely? This mysterious object, traveling at 26 kilometers per second, defied every law of physics we thought we understood, accelerating away from the sun without any visible explanation. Here's the mind-blowing part. Some of the world's top scientists now believe we may have just witnessed our first encounter with alien technology. Did you know that Oumuamua is still the only confirmed interstellar object we've ever detected, and it's already gone forever? Oumuamua initial detection. On October 19, 2017, the universe delivered humanity its first confirmed interstellar messenger, and it caught us completely off guard. The Pan-STARRS telescope in Hawaii was conducting routine asteroid surveys when astronomers Robert Warwick and his team spotted something extraordinary streaking across the starfield at unprecedented velocity. This wasn't just another space rock cataloged in their database. It was moving too fast, coming from the wrong direction, and following a trajectory that immediately screamed outsider to anyone familiar with solar system dynamics. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, recognizing that this discovery would fundamentally change our understanding of what lurks in the spaces between stars. Within hours of the initial detection, telescopes around the world were frantically tracking this mysterious visitor as it hurtled past Earth at 26 kilometers per second, speeds that dwarfed anything gravitationally bound to our sun. The object had already completed its closest approach to our star and was racing toward the outer solar system, giving scientists only a precious few weeks to study it before it vanished forever into the cosmic void. What made this discovery truly groundbreaking wasn't just that Oumuamua came from another star system, it was the first interstellar object ever detected passing through our cosmic neighborhood, opening an entirely new field of astronomy and raising profound questions about what else might be drifting silently through the galaxy, undetected by our current observation methods. Classification challenges. The moment scientists began analyzing Oumuamua's properties in detail, they realized they were dealing with something that defied every classification system developed over centuries of astronomical observation. Initially tagged as Asteroid A/2017 U1 based on preliminary observations, the object quickly demonstrated characteristics that challenged this hasty designation. Unlike typical asteroids which maintain relatively stable brightness patterns as they rotate, Oumuamua's luminosity varied dramatically by a factor of 10 as it tumbled chaotically through space, suggesting an extremely unusual elongated shape that was unprecedented in solar system astronomy. Even more puzzling, despite approaching within 0.25 astronomical units of the Sun, close enough to vaporize surface materials on most comets, it displayed absolutely no coma, tail, or any other signs of outgassing that should accompany such solar heating. NASA's Jet Propulsion Laboratory and international astronomy teams spent months in heated debates, frantically analyzing spectroscopic data and photometric measurements while flip-flopping between asteroid and comet classifications as new observations contradicted previous assumptions. The confusion reached such levels that by 2018, the International Astronomical Union was forced to create an entirely new category, officially designating it 1I/Oumuamua, the 1I indicating the first confirmed interstellar object, and establishing a new nomenclature system for future discoveries. This classification nightmare highlighted how woefully unprepared our taxonomic systems were for objects originating beyond our solar system, forcing the scientific community to acknowledge that Oumuamua might represent a completely unknown class of celestial bodies formed under conditions and processes entirely different from anything occurring within our sun's gravitational influence. Trajectory analysis. When astronomers reverse-engineered Oumuamua's cosmic journey using sophisticated orbital mechanics calculations, they uncovered an epic tale spanning potentially millions of years across the vast emptiness of interstellar space. The comprehensive trajectory analysis performed by international teams at ESA's European Space Operations Center and NASA's Jet Propulsion Laboratory revealed that this interstellar wanderer had been drifting through the galaxy long before our solar system had even settled into its current configuration of planets and orbital resonances. Using precise astrometric measurements from multiple observatories, Researchers initially calculated that tracing its path backward pointed toward the direction of Vega in the constellation Lyra, one of the brightest stars in our night sky. However, deeper analysis incorporating proper motion corrections and galactic rotation models revealed a far more complex story that challenged simple origin theories. The object would have needed approximately 600,000 years to travel from Vega's current position to reach our solar system, yet stellar motion calculations proved that Vega wasn't located in that position 600 millennia ago due to the constant movement of stars through galactic space. This startling discovery proved that Oumuamua was a true galactic nomad with no clear stellar home, having wandered through multiple stellar neighborhoods during its cosmic odyssey. Its hyperbolic trajectory, a mathematically defined path that curves around the Sun once before heading back to interstellar space forever, indicated approach speeds of 44 kilometers per second relative to our Sun at perihelion. Unlike the elliptical orbits of comets and asteroids gravitationally bound to our star, Oumuamua possessed more than enough kinetic energy to escape permanently into the cosmic wilderness, never to return to our solar system again. Photometry and shape analysis. The light measurements of Oumuamua revealed, honestly, the most bizarre shape ever recorded for any natural object in our solar system. Photometric observations conducted by observatories all over the globe, including the Very Large Telescope in Chile and Gemini Observatory in Hawaii, showed brightness variations that, well, could only be explained by an extremely elongated form. Scientists calculated that Oumuamua was at least 10 times longer than it was wide, with dimensions roughly 400 meters by 40 meters, kind of resembling a cosmic cigar tumbling end over end through space. Dr. Karen Meach from the University of Hawaii led international teams analyzing these light curves, discovering the object completed one full rotation every 7.3 hours. The extreme aspect ratio was totally unprecedented. No known asteroid or comet even came close to such proportions. Some researchers, including Dr. Shmuel Bieli, proposed it might be even flatter, resembling a cosmic pancake rather than a cigar, which honestly would make it even more unusual. The surface appeared reddish, similar to objects in the outer solar system that have been darkened by cosmic radiation over billions of years. However, Oumuamua reflected only about 4% of incident sunlight, making it darker than charcoal. This combination of extreme elongation, dark surface, and rapid tumbling motion created a unique signature that really challenged existing models of how small bodies form and evolve in space, suggesting formation processes completely unlike anything occurring in our solar system. Acceleration anomaly. The discovery that, honestly, shattered every conventional explanation came when precise tracking revealed Oumuamua was accelerating away from the Sun in ways that just defied physics. Dr. Marco Micheli and his international team published their groundbreaking findings in Nature journal in June 2018, documenting a small but measurable non-gravitational acceleration of approximately 4.92 times 10 to the minus 6 meters per second squared. This wasn't measurement error. Multiple independent observations confirmed that Oumuamua was actually speeding up as it moved away from our star. For typical comets, acceleration like this makes perfect sense. Frozen gases sublimate near the Sun, creating jets that act like tiny rocket engines. However, Oumuamua showed absolutely no signs of this outgassing activity. No visible coma, no tail, no gas emissions detectable by any instrument. The Hubble Space Telescope conducted follow-up observations that confirmed the anomalous motion while ruling out systematic errors or unknown forces. This acceleration was too large to be explained by solar radiation pressure alone, yet too small to be caused by gravitational influences from planets or other bodies. The mystery deepened when scientists realized that whatever was causing this acceleration appeared to be acting continuously and smoothly, rather than in bursts typical of comet outgassing. This unprecedented behavior forced astronomers to consider possibilities they had never seriously contemplated. Either Oumuamua represented a completely unknown type of natural phenomenon, or well, something artificial was responsible for its strange motion through our solar system. Spitzer observations. NASA's Spitzer Space Telescope conducted humanity's final attempt to solve the Oumuamua mystery before the object disappeared forever beyond the reach of Earth's instruments. During November 2017, this infrared observatory pushed its capabilities to the absolute limit. conducting some of the most sensitive thermal measurements ever attempted on such a distant small object. Dr. Davide Farnocchia and his team at JPL analyzed the resulting data, hoping to detect the warm signatures of outgassing that might explain the acceleration anomaly. Instead, Spitzer's observations only deepened the puzzle. The telescope detected virtually no thermal emission from Oumuamua, setting strict upper limits on any dust or gas production. If the object were behaving like a normal comet, even minimal outgassing should have created detectable infrared signatures, as solar heating warmed expelled material. The absence of such emissions meant that if outgassing was responsible for the acceleration, it had to be composed of materials completely invisible to infrared detection. Spitzer's measurements also refined estimates of Oumuamua's size and reflectivity, suggesting it was smaller than initially calculated, possibly only 100 to 200 meters in its longest dimension. This smaller size would actually amplify any outgassing effects, making the lack of detectable emissions even more mysterious. The final Spitzer observations in January 2018 showed Oumuamua continuing its anomalous acceleration while remaining thermally invisible, leading scientists to conclude that conventional comet behavior could not explain this object's properties and motion through our solar system. Artificial origin hypothesis. When every natural explanation failed, Harvard University's Professor Avi Loeb and postdoctoral researcher Shmuel Bialy proposed the unthinkable in a paper published in the Astrophysical Journal Letters in October 2018. They suggested that Oumuamua might actually be artificial, specifically a light sail created by an extraterrestrial civilization. This hypothesis, honestly, elegantly explained the acceleration anomaly. A thin, flat object could be pushed by solar radiation pressure without requiring any outgassing. For this mechanism to work, Oumuamua would need to be incredibly thin, less than 1 millimeter thick, while still maintaining its observed dimensions. Loeb proposed it could be debris from alien technology, possibly millions of years old, just drifting through space like cosmic junk from a long-dead civilization. The light sail hypothesis explained not only the non-gravitational acceleration, but also the object's extreme elongation and its unusual tumbling motion. Dr. Loeb argued that extraordinary claims require extraordinary evidence, but, extraordinary evidence also requires extraordinary hypotheses. The scientific establishment reacted with fierce criticism, with many astronomers arguing that invoking alien technology violated Occam's razor, the principle favoring simpler explanations. However, supporters pointed out that dismissing the possibility without proper investigation could actually represent a form of cosmic prejudice. The debate raged across scientific journals and conferences, with researchers split between those demanding more conventional explanations and others willing to consider that humanity had encountered its first piece of alien technology, even if we couldn't definitively prove it. Dark comet theory. Dr. Daryl Seligman from the University of Chicago proposed a revolutionary alternative that really challenged our understanding of comet composition and interstellar chemistry. The dark comet hypothesis, which was published in the Astrophysical Journal back in 2020, suggested that Oumuamua could actually be made mostly of frozen molecular hydrogen. In the extreme cold of interstellar space, where temperatures are around 14 Kelvin, hydrogen can freeze into solid ice that would stay stable for millions of years. As Oumuamua got closer to our sun, this hydrogen ice would sublimate directly into gas, but unlike water vapor or other typical comet materials, hydrogen gas is almost completely invisible to most astronomical instruments. This invisible outgassing could explain the mysterious acceleration without creating any visible coma or tail. The theory goes on to suggest that Oumuamua formed billions of years ago in a giant molecular cloud. Those vast regions of space where gas and dust come together before forming new stars and planetary systems. These environments could create really unique conditions for hydrogen ice to build up, making objects unlike anything we've seen in our own solar system. Seligman's calculations showed that a hydrogen iceberg about the size of Oumuamua could stay intact during its journey through interstellar space, and provide enough outgassing to explain the observed acceleration. This hypothesis opened up the possibility of an entirely new class of interstellar objects that might be drifting undetected all over the galaxy, basically invisible to our current observation methods, because their outgassing doesn't produce any visible signatures that our telescopes can pick up. Dark comet classification. The implications of the dark comet theory went way beyond just Oumuamua. It could totally revolutionize the way astronomers classify small bodies in space. Researchers at NASA's Jet Propulsion Laboratory started developing new classification systems to account for objects that show non-gravitational acceleration, but without any visible activity. Scientists began to propose distinguishing between small dark comets like Oumuamua, which came from interstellar space, and potentially large dark comets that might actually exist within our own solar system, just unrecognized up until now. Dr. Daryl Seligman and his colleagues even identified several objects in the solar system database that showed unexplained acceleration without obvious outgassing, suggesting that dark comets might be way more common than we ever imagined. The new classification parameters included things like thermal emission signatures, spectroscopic properties, and acceleration magnitudes that are really different from what we see with traditional comets and asteroids. This new framework suggested that maybe our telescopes have been missing a whole population of hydrogen-rich objects simply because our detection methods are tuned for water-ice comets and rocky asteroids. The European Space Agency even started to include dark comet detection protocols in their future mission planning, realizing that interstellar visitors could be a lot more common than just the single confirmed case of Oumuamua. Some researchers estimated that if the dark comet hypothesis is correct, the galaxy could have billions of these invisible objects, creating a hidden population of interstellar wanderers that occasionally pass through planetary systems without us even noticing. This whole idea really changes our understanding of how material is distributed across the galaxy, and it suggests that the space between stars could be way more crowded with small bodies than our astronomical models had predicted. Scientific debate. The Oumuamua controversy has basically split the astronomical community into competing camps, each one defending some pretty radically different interpretations of the same data. Team Natural, led by researchers at NASA's Goddard Space Flight Center and the European Southern Observatory, insists that conventional physics has to explain the acceleration anomaly, and they propose things like outgassing of common volatiles or internal changes during solar heating. Then there's Team Artificial, led by Harvard's Avi Loeb and backed by researchers from Tel Aviv University, who argue that the light sail hypothesis deserves serious scientific consideration, and shouldn't just be dismissed because people are skeptical about extraterrestrial explanations. Team Dark Comet, centered around researchers at the University of Chicago and Yale University, is pushing the hydrogen iceberg theory and working on ways to detect similar objects. The debate has been going strong in top scientific journals like Nature, Science, and the Astrophysical Journal since 2018, and honestly, each new analysis seems to make the mystery even deeper. Dr. Alan Fitzsimmons from Queen's University Belfast leads the skeptics, saying that these exotic explanations go against scientific principles, while Dr. Abraham Loeb's supporters counter that extraordinary evidence demands extraordinary hypotheses. Recent studies have even found more solar system objects with similar properties, which could support the dark comet classification. The scientific process is working exactly as it should. Competing hypotheses are driving new observations and new theories. Whether Oumuamua was natural, artificial, or something totally unprecedented, it's already changed astronomy by showing that interstellar objects can really challenge our most basic assumptions about the universe, forcing scientists to broaden their frameworks for understanding cosmic phenomena. So, there you have it. Oumuamua is still one of the greatest mysteries in modern astronomy, challenging just about everything we thought we knew about interstellar objects. Whether it was a natural dark comet, alien technology, or something completely unprecedented, this cosmic visitor has forever changed the way we see our place in the universe. What's your theory? Was Oumuamua our first glimpse of extraterrestrial engineering, or does nature still have more surprises up its sleeve? Drop your thoughts in the comments below. I read every single one. And if you're fascinated by these mind-bending space mysteries, go ahead and smash that subscribe button and hit the bell icon so you never miss the latest discoveries from InnoVision Tech. Until next time, keep looking up. A cosmic object 100 times bigger than anything we've ever tracked just entered our solar system, and it looks like it's hunting a smaller, equally strange visitor that arrived just weeks before. On September 12, 2025, astronomers witnessed an impossibility. Two massive, anomalous bodies arriving from opposite ends of the galaxy, set to rendezvous near the sun. The odds are non-existent, and the evidence points not to a comet, but to a fortress. Let's explore this together. The Swan's dramatic arrival. What does it look like when the impossible streaks across the sky? On September 12, 2025, we found out. The SWAN instrument, a solar wind anisotropy sensor aboard the SOHO spacecraft, flagged a new object blazing a path through the inner solar system. The first data sets, analyzed by teams led by SOHO project scientist Bernhard Fleck, were staggering. The object possessed a tail stretching nearly 2.5 degrees across the sky, about 5 times the width of a full moon. To put that in perspective, a tail of that magnitude suggests a hydrogen outgassing rate hundreds of times greater than a typical long-period comet. Its initial brightness was clocked at magnitude 7.4, luminous enough to be seen with backyard telescopes from a distance of over 150 million kilometers. This wasn't some faint smudge. This was a spectacle. News ignited across astronomy networks. And just 2 days later, an amateur observer captured a jaw-dropping image showing a streak so immense it barely fit the camera's frame. It was too big, too bright, and its trajectory was already looking far too precise. The raw energy output required to generate such a visible display at that distance was the first red flag that this was something entirely new. Official recognition and growing mystery. How do you classify something that breaks all the rules? By September 13th, the Minor Planet Center, where figures like the late, great Gareth V. Williams once vetted such discoveries, made it official. The object was designated C/2025 R2 or SWAN, acknowledging the instrument that found it. That official stamp kicked off a global frenzy. Its initial orbital eccentricity was calculated at over 0.999, confirming it as a long-period visitor on a path that would take millennia to repeat. The sheer size and luminosity created a wave of disbelief. Veteran astronomers had to reach back to the legendary comet Hale-Bopp of 1997, a comet with a nucleus estimated at 60 kilometers in diameter, to find a worthy comparison. SWAN, however, was already outshining Hale-Bopp at a similar distance from the Sun. It was slicing through the constellation Virgo, growing brighter as it approached its perihelion of roughly 1.0 astronomical units, the same distance as Earth is from the Sun. The question shifted from what it was, to why it had arrived right now with such perfect timing. The numbers didn't just suggest a large object, they hinted at an impossibly active one. The cosmic coincidence. Some things are so unlikely, they stop looking like a coincidence. C/2025. R2 SWAN is not the only strange visitor this October. Days before, another object, 3I/Atlas, was already inbound from a completely different part of the sky. Imagine a celestial map. SWAN's path traces back from Aquarius, while Atlas entered from the direction of Sagittarius. Yet, both are set to reach their closest pass by the Sun within the same 10-day window. For Atlas, that's October 17th at a distance of 1.36 astronomical units. For SWAN, it's just 3 days later, around October 20th, at a much closer 1.0 astronomical units. Their perihelion points are separated by only about 50 million kilometers, closer than Mars ever gets to Earth. The geometry is what's truly stunning. Both are on steeply inclined orbits, with SWAN's path tilted more than 60 degrees and Atlas nearly 90 degrees to the ecliptic plane. As orbital dynamicist Paul Wiegert would tell you, the statistical probability of this kind of synchronized arrival from such different trajectories is infinitesimally small. It's a corridor in space-time that seems to have been deliberately targeted. This is not random chance, it is a rendezvous. Atlas breaks the rules. So what do you do when an object's very existence kind of violates physics? 3I/Atlas, discovered by the University of Hawaii's Asteroid Terrestrial Impact Last Alert System Survey, which was headed by Larry Deneau, first got attention for its composition. Early spectrographs showed a body dominated by nickel, with almost no iron at all. This, honestly, directly contradicts our knowledge of asteroids, which nearly always feature iron-nickel alloys in, pretty predictable ratios, but the anomalies didn't stop there. Instead of water vapor, Atlas's coma was surprisingly pumping out carbon dioxide, with its 4.3 micron spectral line dominating every reading. But the real smoking gun was its movement. Observers logged 3 distinct non-gravitational accelerations, on July 29th, August 14th, and August 30th. These weren't smooth pushes. They were sharp bursts, delivering a delta V of several meters per second each time. The behavior was so precise it was dubbed thrust mix modulation, which, honestly, implies a controlled engine burn that was adjusting its composition output. The data held up across multiple observatories, painting a pretty clear picture. This thing was under its own power and, yeah, on a mission. The physics just honestly left no other room for interpretation. Swan, the fortress. If Atlas is a nimble drone, then Swan is, well, a battleship. The scale of C/2025 R2 is hard to even comprehend, but honestly it's the data that paints a pretty radical picture. One that has driven speculators like Harvard's Avi Loeb to consider similar theories for other objects. It all began with reflectance data. Swan's core has an albedo, or reflectivity, that's far higher than a typical dark comet nucleus, actually matching the signature of polished metal. Some analysts argue it fits a nickel-cobalt blend, which is an alloy used for its immense strength. Then, reports started coming in about a silvery halo around the nucleus, an anomaly some interpret as a plasma envelope or maybe even an electromagnetic shield. This is where it earned the nickname the Fortress. Unlike Atlas, Swan appears steady and honestly invulnerable, refusing to fragment as it nears the sun. Even its tail shows evidence of microthrusts, tiny rhythmic pulses at a consistent frequency that, frankly, defy natural outgassing. Add in its 22,554-year orbit, and you have an object that appears to be ancient, armored, and well, on a deliberate, powered course. It isn't just passing through, it's arriving. Mission theories. When a 1 in a trillion coincidence happens, you kind of have to consider it wasn't a coincidence at all. The timing, the geometry, and all this anomalous behavior have really fueled mission theories. One is a scheduled refueling run, an idea that actually fits with concepts of advanced astroengineering proposed by physicists like Freeman Dyson. A more unsettling theory is, well, an intervention. A rendezvous to neutralize a malfunctioning unit. The estimated power levels, Atlas at 10 gigawatts and Swan at a staggering 10,000 gigawatts, suggest energy reserves needed for active maneuvering, not just passive drifting. There's also the audit chain scenario that 1I/Oumuamua in 2017 and 2I/Borisov in 2019, both on hyperbolic trajectories, were scouts. Atlas was a more advanced follow-up, and now Swan is the main event. In every case, the sun is the rendezvous point, the most powerful energy source in the system. The evidence really forces us to ask, if this is a mission, what is the objective? These aren't just rocks, they're actors on a cosmic stage. Ancient connections. An orbit of 22,554 years is, a link to a different chapter of human history. The last time Swan would have passed was around 20,000 BCE, right at the peak of the last glacial maximum. This is where the story connects to Göbekli Tepe, a site in Turkey built around 9500 BCE. Researcher Martin Sweatman has proposed a controversial theory that its pillars are an astronomical observatory, recording a cataclysmic comet impact that triggered the Younger Dryas climate shift. He argues that Pillar 43 specifically tracks a long-period celestial object. Mainstream archaeologists, including the site's original lead excavator Klaus Schmidt, have strongly disputed this, maintaining the carvings are symbolic. Still, the timing is, hard to ignore. If Swan is on a recurring path, its last visit coincided with a transformative period for humanity. Whether that is a coincidence or a clue remains a fiercely debated question. It adds a layer of mythic resonance to an unbelievable event, suggesting we may have seen this visitor before. The blackout window. Just when things are about to get interesting, the curtains are being drawn. From October 8th to 18th, every major ground-based observatory from the Very Large Telescope in Chile to the Keck Observatory in Hawaii is effectively blind. This solar conjunction is predictable. What isn't normal is the alleged response. According to inside sources, memos from US Space Command and the ESA have directed teams to suspend all imaging. The official rationale is to protect sensitive optics from the sun's glare. But that doesn't explain why radar facilities like Arecibo's successor, which are immune to solar glare, would also be ordered to stand down. This specific detail makes the official story fall apart. Proposals for alternative observation methods have reportedly been denied, and data requests have been delayed. Several telescope allocation reviewers describe explicit orders to avoid public statements. The result is a forced information vacuum at the most critical moment. Underground resistance. When the official channels go dark, The people build their own. The blackout order may have silenced major observatories, but it ignited a firestorm in the amateur and independent astronomy communities. Veteran tracker Bill Gray put out a call to arms across public forums: keep your scopes on the sky, log everything, and share the raw data on open-source servers. A distributed web of astronomers with powerful 14 and 20-inch telescopes answered. Collectives like the Ibero Tracker Group in Europe began pooling their photometric and astrometric data feeds. Leaks suggest plans to use radio telescopes to pierce the solar glare. This grassroots effort has become the only real-time source for what might happen during the blackout. It's a powerful narrative of decentralized science, a global network ensuring no data disappears. When Swan and Atlas re-emerge, the first images confirming their post-perihelion behavior might come from a garage, not a government lab. This has become a testament to citizen science. Power estimates and implications. Let's talk about the energy required to make these objects move. Atlas's accelerations required a power source of around 10 gigawatts, the output of 10 large nuclear power plants, but that is dwarfed by Swan. Based on its luminosity, its suspected micro-thrusts, and the energy needed for a plasma shield, the Fortress could be wielding something close to 10,000 gigawatts. That is more raw output than the entire power grid of planet Earth combined. On the Kardashev scale, a civilization capable of controlling energy on this level is approaching Type 1 status. These are not trivial anomalies. These figures are the hardest evidence to dismiss as natural phenomena. They move the conversation from astronomy into astro-engineering and contact theory. The sheer physics involved screams that we are dealing with a technology far beyond our own, powered by a source we can't yet comprehend. This is the bottom line that makes the engineered object hypothesis so compellingly logical. The facts are as clear as they are unnerving. Two anomalous objects defying all statistical odds have entered our solar system on a synchronized path. One appears to be a powered drone, the other an armored fortress. They are scheduled for a close encounter during a 10-day window where they will be conveniently hidden from our best telescopes by the sun, accompanied by an official top-down order for radio silence. This has forced the search for answers into the hands of a global network of citizen scientists. Are we witnessing a cosmic accident, a pre-planned mission, or something else entirely? Whatever the truth is, we are about to find out. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching InnoVision Tech. There are images that show us beauty, and there are images that show us truth. This one does neither. At first glance, it looked like a failure, a photograph that refused to focus, but behind that blur was something extraordinary. The third interstellar object ever observed, 3I, Atlas, currently racing through our solar system. What does this mysterious image actually reveal? What secrets are hidden in the data that our eyes can't see? Let's explore this together. How do you photograph something that refuses to stay still? Capturing 3I Atlas wasn't like shooting an ordinary comet. It moves too fast and shines too faintly for any normal exposure to work. By the time a telescope collects a few seconds of light, the object has already traveled thousands of kilometers, moving at a blistering speed of roughly 12 kilometers per second relative to the sun. A single frame would show nothing but a soft, meaningless streak. To overcome that, as orbital dynamics expert Davide Farnokia can attest, the telescope had to chase it. Tracking software predicted the comet's path second by second, adjusting the mount in near real time to keep the magnitude 17 object perfectly centered on the sensor. For context, that is over 25,000 times fainter than the faintest star visible to the naked eye. As a result, the stars in the background blurred into trails, but 3I Atlas held its position. What looks like a still blur in the final image is actually motion perfectly cancelled out. The challenge is immense. Even a tiny error in the predicted trajectory would smear the object into invisibility. This wasn't just a photo, it was time made visible, a precise balance between the comet's impossible speed and the telescope's relentless pursuit, a feat of engineering that astronomers at the Minor Planet Center work to perfect daily. What do you do when an object's shape is also its shadow? In the image, 3I Atlas doesn't show a surface. There's no crisp edge, no nucleus shining at the center. What we see instead is an outline that refuses to stay defined, a gray body that fades into itself. The elongation is unmistakable, smooth at one end, uneven at the other, with a length-to-width ratio estimated to be at least 3:1. This shape has puzzled everyone studying it, including specialists in cometary structure like Karen Michio, whose work on one Oumuamua set the precedent for analyzing such faint signals. If it were a normal comet, we'd expect a rounded head and a tapering tail. This is different. The frame shows a body that seems evenly stretched, almost like a cylinder. The brightness peaks slightly toward one side, suggesting it might be spinning rapidly on a 7 to 9 hour rotation period, blurring its features the way a long shutter smooths moving water. The faint light we see isn't emission, it's reflection scattered through a thin layer of ejected material, too tenuous to be called a proper coma. This object's form is defined more by its interaction with light than by its physical boundaries. The shape stands as a physical clue wrapped in uncertainty geometry without a surface. What can a lack of color tell us about an object's past? When astronomers processed the raw images of 3I Atlas, they found something curious: no real color. Most comets show at least a hint of tone, like a greenish halo from cyanogen gas. But this object gives almost nothing. Across visible wavelengths from 400 to 900 nanometers, its spectrum flattens into a neutral gray. As planetary scientist Alan Fitzsimmons has explained with similar objects, this absence tells us 3I Atlas isn't actively outgassing in any strong way. Instead, we are seeing pure reflection bouncing off a surface so dark it has an albedo, or reflectivity, of only 2 to 3%, literally blacker than asphalt. Over millions of years drifting between stars, its surface has been bombarded by cosmic rays, baking carbon molecules into complex dark organics called tholins. These materials absorb almost every wavelength of light, combining into a neutral gray when seen from a distance. A slight rise in the infrared spectrum suggests the presence of carbon dioxide ice just below the crust, but the signal is incredibly weak. For an interstellar object, that lack of vibrancy isn't emptiness. It's age, a testament to an eons-long journey through the void. This is the color of endurance. So, how do you prove something exists when it's barely even there? That's the puzzle with 3I Atlas. It lives right on the edge of what our detectors can actually prove. In its raw data, the comet is like a whisper above the background noise, with a signal-to-noise ratio just barely clearing the 3 sigma statistical threshold that's required for a confirmed detection. But, as astronomer David Jewett, a pioneer in discovering faint objects in the Kuiper belt, would confirm, the difference between random static and a real object is consistency. Real light behaves with intent. It repeats and holds a pattern where chaos simply can't. That's what makes the 3I Atlas image meaningful. Across exposures, the faint streak appears in the exact same coordinates predicted by orbital models, delivering just a few dozen photons per minute to the detector. Its brightness curve remains stable despite atmospheric shifts and thermal noise from the camera itself. The data isn't just faint, it's fragile, requiring mathematical reconstruction to separate the comet's photons from random ones. This process, called image stacking, is less like taking a picture and more like building one from scratch over hours of observation. The final image exists only after millions of calculations reduce chaos into geometry. It's an image at the threshold of certainty, not sharp enough for comfort but too consistent to dismiss. What happens when your discovery refuses to be discovered? Once the image of 3I Atlas was assembled, it didn't behave like anything the calibration software was designed for. Algorithms that measure coma, nucleus, and tail couldn't settle on a pattern. The numbers diverged. In data terms, that means the target is either unstable or the physics behind it doesn't fit our templates. As interstellar object expert Matthew Knight has noted in his research, these visitors often challenge our models. 3I Atlas breaks the logic. Its confirmed hyperbolic orbit, with an eccentricity of roughly 1.1, proves it's not from around here. It behaves like something between 1I Oumuamua, which had no visible coma, and 2I Borisov, which displayed a textbook coma even at 3 AU from the Sun. Its blur is too diffuse to be a solid asteroid, but too clean to be an active comet. That ambiguity makes classification nearly impossible using standard cometary models. The The picture isn't wrong, it's just showing us a kind of object our instruments and our scientific language weren't built to categorize. It exists in a scientific gray area. When an image can't explain itself, how do you make it talk? Mathematics takes over. The frame of 3I Atlas is too faint for traditional analysis, so scientists like Robert Warwick, the discoverer of Oumuamua, turned to numbers to extract what the light couldn't say. Every pixel becomes a coordinate, every shade of gray a probability. The first step is motion modeling through precise astrometry. Plotting its position across nights confirms its hyperbolic trajectory and its 12 kilometers per second velocity. The math is certain. It's moving too fast to ever be captured by our sun. Next comes brightness fitting, or photometry. The faint gradient along its length is modeled to estimate its shape and rotation. Simulations show that if the nucleus is elongated with a 3-to-1 ratio, a slow tumble could recreate the uneven brightness we see. The math detects a tiny variation the eye can't. Even the blur itself becomes measurable through a process called deconvolution, which mathematically reverses the distortions, separating motion blur from its intrinsic shape. The image shows uncertainty, but the equations describe exactly why it must look that way. Is that a real shape, or just a ghost in the machine? Every astronomical image has them. Cosmic rays can leave small flares, and tiny tracking errors can accumulate and masquerade as structure. When the first image of 3I Atlas was released, that question appeared immediately. How much is the comet, and how much is the instrument? The cylindrical blur could, in part, be a subtle elongation caused by the camera compensating for motion and noise, an effect related to the telescope's point spread function. A residual drift of just half a pixel per exposure, when multiplied by dozens of frames, creates a false extension. But not all anomalies vanish under scrutiny. As astronomer Wesley Fraser has explored in his work, consistency is key. When the images were independently processed using different software, the same general elongation remained. The angle of tilt and brightness gradient persisted. That argues against coincidence. If distortion were the only cause, its signature would shift between instruments or processing techniques. Instead, the shape repeated itself, asserting its bizarre geometry through the limits of our observation. At some point, what do you call something that refuses to be named? The discussion around 3I Atlas stopped being about what it looked like and became about what it refused to be. It wasn't a traditional comet, lacking a tail. It wasn't an asteroid. Its light curve was just too smooth and its spectrum way too neutral. It presented something in between, a blur that really resisted interpretation. The data which experts like Amy Mainzer from NASA's NEOWISE mission used to classify thousands of small bodies paints a picture of contradiction. The brightness curve, varying by less than 10%, suggests a single, stable body, yet its slight asymmetry hints at a slow tumble, or maybe even fragments orbiting a shared center. Its trajectory confirms an interstellar origin, a path that ensures it will never return. That certainty of escape is, honestly, the only familiar thing about it. It forces us to confront the uncomfortable idea that seeing isn't the same as knowing. Sometimes, the clearest image possible is one that stubbornly refuses to resolve. It challenges not just our technology, but our very system of classification. So, if it defies every category we have, what could it be? This is where scientific observation meets informed imagination. 3. Atlas sits perfectly between the two prior interstellar visitors. 1I, Oumuamua, was sharp and fast. 2I, Borisov, was almost too typical. 3I Atlas is neither, behaving like a memory of both. It's too diffuse to be solid rock, too clean to be a classic comet. It exists in a gap where our definitions just totally fail. It's objects like this that inspire radical new ideas. When data stops fitting patterns, thinkers like Loeb have argued that we must be open to unconventional explanations. While he was referring to Oumuamua, the principle really applies here. Is this a new type of dark comet that outgasses materials our instruments can't detect? Could it be a fragment from a tidally disrupted exoplanet, an entirely different class of object? Is it 90% asteroid and 10% comet, or something else entirely? The object is a scientific mystery box. The blur is both evidence and absence, a confirmed detection that withholds its identity, reminding us that our categories are only conveniences, not cosmic truths. What is the final story of a visitor we only glimpse as it leaves forever? When the light from 3I Atlas fades from our view, the photograph will remain, a faint smear in an archive. In most sciences, this would be dismissed as inconclusive. In astronomy, it becomes the most honest evidence possible. As astrophysicist Gregory Laughlin might agree, a blur is what happens when the scale of the universe meets the limits of our focus. Everything measurable about 3I Atlas, its speed, its path, its rotation, its chemical hints, exists inside that faint streak. Its weakness is its strength. It forces meaning to come from physics and mathematics rather than from simple appearance. Soon, it will leave our system entirely, receding back into the interstellar dark. The blur we have is not the beginning of a study but the end of accessibility. It's not a picture of a destination, it's a snapshot of passage. It is a faint fingerprint left on the window of our solar system by a traveler just passing through. 3I Atlas was never truly seen. It was measured by its blur, and that is the clearest image we could ever hope for. 3. I Atlas is a visitor that escapes our definitions, a blur that exists in the thin space between what we know and what we can only imagine. What do you think is hiding within that faint smear of light? Share your theories in the comments section below. We're always curious to hear what you think. If you want to continue exploring the universe's greatest unsolved puzzles with us, don't forget to like, subscribe, and hit the bell icon so you won't miss our next deep dive. Thank you for watching InnoVision Tech.